Yeah, it's 9:04. We can start now. So, hello everybody for the third talk or presentation about quantum communications with a focus on time synchronization in quantum communication networks. Our speaker today is Christer Schalm. Christer Schalm is an experimental quantum physicist working at the National Institute of Standard and Technology, NIST, since 2012. His research focuses on studying the fundamental properties of light to develop new quantum techniques. He received his PhD in physics from the University of Toronto in 2010 and subsequently performed postdoctoral work at the Institute of Quantum Computing in Waterloo. Wow. I know this institute because uh, uh, I think this is one is built by that rich guy who did
BlackBerry.
research in motion. Yeah, BlackBerry, exactly. And Crystal work on entanglement has received widespread international recognition. That's great, Crystal. Excellent. And Crystal, when he is not in the lab or sharing his love of science, which is very obvious, he can be found swing dancing. I like dancing too, Crystal. I used to take
Okay.
lessons. I used to take lessons with in Arthur Murray lab. Arthur, not lab, Arthur Murray studio.
Yeah, Arthur
And,
Murray.
yeah, and they taught me swing. I got actually up to bronze in a swing. Yes, hustle, cha-cha, all of this. So thank you very much, Christopher, for accepting to make the presentation, and the floor is yours.
All right, well, thank you so much. I promise there won't be any dancing in this particular talk. But just to start with, so I'm going to tell you about some of the work we're doing here at NIST towards building, I would call, next generation quantum networks. And, for this talk, I have a number of things to discuss, but I would much rather us actually have a conversation. So please feel free at any time to just unmute yourself and ask questions as we kind of go along. And we can actually just, I think that's a more productive way to do things. So today I'll be telling you about, again, some of the work we're doing towards these kind of next generation quantum networks. Today I really want to showcase, or at least tell you, like, some of the how like the quantum networks we're going to try to build, how they work, what they're useful for, and what the major types of timing issues we will have with them. And unfortunately, well, just to kind of build everything up, it's going to take a while to get to the timing stuff. Because I have to front load, the first part will be more like a tutorial, and then we'll get into how we actually do things. So to get started with, I'm here in Boulder, Colorado, and so this is the NIST campus right here, and we're right next to the Rocky Mountains, and that's about a mile and a half behind our campus. You can go hiking. Over here is the NOAA. That's the where a lot of our weather research is done, and then on this side over here, I don't know if you can see my mouse. Yeah, this is our the NIST campus. And so here's some folks within our group that are kind of currently working on the quantum networking project. Was a part of Dr. Sewu Nam's group, and also now currently with Richard Miron's group. Sewu Nam pioneered a lot of detector research, and unfortunately, passed away earlier this year, due to brain cancer. And so that's been a bit of a shock for our group, but Sewu, a lot of his work is strongly represented in this talk. So just to kind of start with, what are we trying to do here in Boulder? Well, we really want to build a scalable quantum network that overcomes loss in order to distribute high quality entanglement that can be used to perform quantum communication protocols with a provable quantum advantage. And we really want to achieve kilohertz rates of entanglement distribution over metro scale regions. And so a lot of this talk is just going to be explaining these terms and what they mean, and what we're trying to do. And to start with, when people talk about what can you use quantum for? Like, what's the, people talk about quantum 2.0, or there's all sorts of terms. There's really three areas that you can kind of lump a lot of stuff that people are trying to develop quantum technologies to do things that you can't do with classical systems that have some kind of quantum advantage. And one is to build better sensors. So can you network clocks together, or increase the precision of, or beat like the standard quantum limit for noise readout or measurements. Quantum computing is the big one in terms of the amount of press it gets and the amount of kind of VC funding. And there's a number of companies around the world that are making strong progress towards this. And finally, we have quantum communication, which is where we'll be focusing primarily on today. And so, can you do things? Usually, it's around security. So, can you do things more securely with quantum? But there's a lot of other kind of sort of spin-off applications for communications as well. And so, when I think about like what gives quantum mechanics its power to have a quantum advantage, there are really three things that we utilize. And the first is the fact that quantum states can't be cloned. And that's what a lot of the current quantum key distribution is. Infrastructure and approaches are based around this idea that you can't make a perfect copy of a quantum state. The second thing that you can take advantage of is entanglement. And in particular, entangled correlations. So if you have two quantum systems that are entangled with one another, or multiple quantum systems entangled with one another, they share correlations that are much stronger than what you can get classically. And it turns out that you can use that to do things like build a quantum computer or build sensors that can beat the standard quantum limit. And so a lot of power comes from these quantum correlations. And the third one is that these correlations that are entangled can be non-local, which means that even over long distances, they can persist. And this can give you new classes of quantum secure technologies that eliminate the need for kind of detailed study of like side channels and detailed models of your devices, because the assumptions come down to you can't send information faster than the speed of light. And if you can't send information faster than the speed of light, then you get these what are called device independent kind of quantum protocols that utilize in some sense all three of these. And that's the type of protocols that our lab really works on. And I won't talk too much about those protocols today, but if people are interested, I can point out multiple resources that to learn more about them. So any objections or thoughts so far, or does this seem like a reasonable set of assumptions for everyone?
I think they're reasonable, but I also have a background in this area, so I might not be representative for the group.
Okay, great. Okay, so if anybody objects or wants to ask questions, just again chime in. So thanks, Judith. So I think for me, one of the big challenges for any quantum or classical network that you're always trying to overcome is loss. You look at single mode fiber, and it is an amazing technology, right? Like the best single mode fiber has almost no loss per kilometer. But unfortunately, that loss scales exponentially. So, you go 10 kilometers, well, then suddenly you have to take that to the power of 10. And if you were to string like a fiber from New York to LA and you wanted to send optical communications on it, the amount of attenuation you get is so great that you would have to somehow to get any kind of reasonable rates of like a few photons out per second on average on the other end. So if the amount of light you'd have to put in one side of the fiber was something like equivalent to take all the photons generated simultaneously by all the stars in the galaxy, somehow cram them into like one end in LA, and then you're going to get a few photons out in New York. So it's everybody has to deal with loss. This is not a quantum problem. This is a networking problem with optics. So classically, all you have to do is you have your signal, and then periodically you just, make a copy and amplify it and keep boosting it as you go along. And this amplification allows you to, kind of maintain signal integrity. And so in most networks, it's like, on the average of about like 100 kilometers-ish, sometimes smaller, sometimes longer, that you need to have these kind of amplification stages in. This is great for classical networks. It's terrible for quantum networks because we cannot clone things. I can't make an exact copy of my signal. So you can't do this amplification. So you have to do something else. So there's two approaches. If you just care about quantum key distribution and you want to make some additional assumptions, then you're going to be relying on these kind of no cloning effects. And so what you do is you replace all these amplification stages with trusted quantum nodes. So you do a key exchange between all these different pairs, and then hope that nobody is like eavesdropping or has physical access to these devices. And so you can set up these trusted nodes and then use that to exchange keys over long distances. I'm not going to be talking about that today. Instead, what we'll be talking more about are what we call quantum repeaters. And these are devices that allow you to overcome the loss and fulfill the role of these kind of amplifiers. So that would be what a quantum repeater does. But before we get into quantum repeaters, I just want to make one last kind of background. I really think, I divide quantum networks up into three kinds of size scales. So if you just care about taking a bunch of quantum processors and linking them together in to make a bigger quantum computer in a data center type system, then you're going to have an architecture that's going to favor really high speed entanglement distribution over very short distances. You don't actually need all the infrastructure you might need for a repeater, but rather you're just trying to link up these processors that are very close together. And that's a promising approach that a number of quantum computing companies are taking to make these little modules of a certain size and then link them up optically. And so this is a very promising approach, and you need a very specific set of network requirements and architecture, and that's also going to depend on the kind of qubits you're preparing. So that's one scale of network. The second is what I would call mid-size network. So think metropolitan, like the size of a city, and there if you want to start connecting up different resources, or do within a city, various types of communication, you might consider another type of architecture that's well suited for that can demonstrate entanglement at high generation rates. And then you've got on the other end what do I consider the long haul kind of quantum backbones that are going to connect cities and states and really long distances. And that can either be through satellites, or it can be through these long range, long memory lifetime repeater systems. And so today we're going to be talking almost exclusively about a way to build a metro-sized entanglement distribution scheme based on repeaters. So the first real proposal for making quantum repeaters is this paper by Dwan, Lukin, Sirac, and Solar. And it's sometimes called the DLCZ scheme after the authors. And we're going to use this protocol. This protocol is the foundation of many of the kind of quantum networks that are being developed right now in the quantum repeaters. And we'll be showing you how to do an all-optical version of them, which is a little bit different than what other folks do. But I'm going to go through a simplified version of how this protocol works now, just so folks are kind of on the same page. And the idea is we want to generate entanglement over long distances, because if you do that, then you can actually use entanglement as a really great resource, either to entangle your quantum computers, or do these kind of next generation quantum secure protocols, or entangle quantum sensors, or even just use the entanglement to teleport quantum information efficiently from one station to another. So our whole goal is to really showcase how you can distribute entanglement over lossy channels and overcome the loss in the fibers. So the way we're going to talk about this DLCZ scheme is we're going to have these two clouds, and they could be any kind of matter-based system. I'm just going to use like an atomic system to start with. And what happens is we're going to prepare both atoms in the excited state. And we're going to wait for some period of time, which is roughly equal to half the amount of time it would take for an atom to decay to the ground state. And what can happen is if one of these if one of these atoms emits a photon, so they both start in the excited state, then if one photon is emitted by an atom and detected, well, this beam splitter here erases information about did the photon come from the top or the side. And I don't know. If those photons are indistinguishable and I get a click here, then all I know is that one of the atoms has decayed. And so what I'm left with is an entangled state of one of these atoms being in the ground state and the other being in the excited state. And there's some kind of phase contribution here, which is related, we'll talk about that more, to the path lengths, the difference in path lengths of these two arms. But detecting a photon here erases information about which atom the photon came from. So anybody have any questions about this? Because everything we talk about from now on is going to be based on that. Okay, so this is the DLCZ. This is the basic idea behind the scheme. And so the current state of the art, just a few months ago, there have been several papers published, and two of them used this DLCZ scheme to start trying to do metropolitan entanglement with systems with memories. The first one, which was published here in Nature, used a very similar scheme to this, where they have these kind of atomic ensembles and that they can use to store a photon in. And they had 3 different locations up to 12.5 kilometers apart. And what they did is they have this kind of central server node that has essentially just the photon on a beam splitter that's up here. And what they can do is, establish entanglement between Alice and Charlie, Alice and Bob, or Bob and Charlie, or Alice and Bob. They have all the different possible combinations. They can establish, 2-party entanglement, not 3-party, but 2-party entanglement. And so these experiments this experiment is very, very impressive, as well as the next one I'm about to talk about. But for both of I'll tell about the next experiment too. So this was done in Hefei in China. And in the Netherlands, Ronald Hansen's group has demonstrated using these kind of nitrogen or I guess these vacancy centers in diamond, being able to entangle, one node that's in Delft and the other is in The Hague, and then they've got sort of this midpoint where they put this kind of beam splitter and do this entanglement generation. So both of these setups use DLCZ. Both are being done in deployed fiber, and both of them, while incredibly heroic and impressive, can barely do anything quantum. So the fidelities of the entangled states are extremely low, like they're around 60 to 66%. So they're not even, they're right at the kind of border of even being able to do what we call entanglement purification to make much better entanglement. And the rates are very low. We're talking, depending on how they run their schemes, millihertz rates of generation. So you have to wait like seconds to thousands of seconds, depending on the types of protocols they're running, to get these bits or these entangled bits out that are, barely quantum. So that's the state of the art right now for making repeaters. is these type of systems. And one of the main limitations, there's multiple things that are limiting them, but all of these schemes in DLCZ, as we'll see in a second, really require interferometric optical phase stability. And that's a very hard kind of requirement to satisfy. And that's one of the things we're working on here at NIST. So this is one approach. This is, I would call, the traditional approach to things. Any questions about these experiments or thoughts so far?
Could you comment anything on what the timing issues were and if they contributed to any of the problems here?
Yes. So there's multiple things going on. So first of all, for both of these systems, the emission rates of all the different systems being able to emit photons is already very, very low. And then they've got very, very lossy channels, which, you know, slows everything down. But in terms of timing, the two big issues, one is you have to make sure that like the photons arriving at this this center midpoint, that the photons arrive at the same time. And so you just need to make sure that the wave packet envelope is the same for both of them. That you can do kind of with a white rabbit precision. So for example, Delft used the white rabbit, and it's more than good enough to compensate for like the fiber drifts, which they estimate, I think, is about 5 picoseconds per minute. And it really, you know, it's easy to get those wave packets kind of aligned with something like white rabbit, or it's not easy, but you can do it. The second thing is there's a phase term here that depends on the joint phase of all the paths involved. And so that's an optical phase. So if you know, change by like lambda by 20 or something, that washes out your, it adds like a decohering effect to the states. And that is where they have, that's a real problem. And that severely limits their ability to, you know, it's really what's limiting the fidelity of their states right now, and especially in the Delft experiment. And so we're trying to get that stability up to, you know, to basically be like 100 times better. So instead of being like a lambda by 20 stability, do like lambda by 500 or something like that. So I'll talk about that in a bit. Does that
Yeah,
make sense, Judith?
is there a timing requirement on the incidence of those to have the, I guess in order to have optical phase control, you need to be like a part in 10 to minus 15 kind of minimum at a second, but you're talking millihertz scales, so maybe you don't need to, just trying to figure out like what kind of clocks could be used to ensure this level of distribution and simultaneous arrival. That's later.
I'm gonna get into that in a little bit more detail.
Okay.
But yeah, that's exactly where we're gonna kind of build up to. So
I'll be
great.
patient. Thank you.
Okay. But yes, good. So that's a good way to kind of set the table for some things. So what we're trying to do is something a little bit different. And I'll take a second to build up there. We want to try to do all of this all optically, and I'll explain why in a moment. But to start with, you can replace your detector with a single photon source and do this in reverse. So now what you do is you start with your atoms in the ground state, you send a photon to a beam splitter, and the photon can either go, you know, in the A mode or the B mode. And it's going to, if it's absorbed in one of these atoms, then what's going to happen is now you don't know which photon absorbed it and got excited. And so now you're left with that same ground excited plus excited ground state. You can just time reverse this whole process and send a photon in to do this if you had a good single photon source. This is really hard to do because getting photons from like an independent source absorbed into an atomic system, that's a problem which is, it's related to transduction. We have to really make sure that the photon is well matched to that system and you have high absorption and low loss and everything else. That's a very challenging thing to do. People are working on it, and there's a lot of things that I think need to be developed around this, but we don't really have great, robust, you know, universal transduction technologies right now. This is like, I think like a 10 to 15 year kind of timeline on the horizon to be able to really be able to do this in a more robust manner. So what we're going to do is, if you don't if you're only worried really about quantum communications, you can play a nice little trick, which is, let's not use atoms. Let's instead replace the atomic systems with an all-optical measurement system. So now you can use a local oscillator that comes in that is incident on like a very transmissive beam splitter. So basically all the light from the A mode, like 99.9% of it goes through. So you don't want to lose your single photon or introduce loss there. But then you can send in a coherent state, just a laser pulse, whose photons or the modes are kind of indistinguishable from this incident photon, and do something like a weak field homodyne measurement. And this acts as a phase reference. And then you can do all of the, to a pretty good approximation, all of the kind of quantum measurements that you need to carry out like a whole range of communication and sensing protocols. And so if you do that, then you can, do your measurements on your entangled states in this kind of form. So that'll allow you to generate entanglement. If you want to do entanglement swapping with this, where you actually, this is kind of the basis for a lot of repeaters, then what we really need to do is, since the photons in some sense are kind of replacing our atomic systems, what we need to do is set up a situation where I have a single photon on the left and a single photon on the right. And then what happens is the photons hit this beam splitter, and now I get entanglement. It's called path entanglement because we're depending on which path the photon takes, is it taking this upper path or this side path? So I can generate entanglement here, and I can also generate path entanglement here. And so I have two photons in the system. I have one photon on the left and one photon on the right. And if it so happens that only one photon goes towards these middle system, or to this like beam splitter here, then and I happen to detect a photon, I don't know if this photon came from the left or the right. So I don't know if it's here in this arm or here in this arm. And if everything about these paths is indistinguishable, then that leaves you in this path entangled state of like a 1, 0 plus 0, 1. Either the photon's in this arm or it's in this arm. And the phase, this e to the I phi, actually depends on the phase difference in these two relative paths. And these can be, long paths. So that's kind of where this optical stability is required. And so if we do this experiment and we get a click on this detector, that puts us in the 1, 0 plus 0, 1 Bell state. That's an entangled state between these two systems. And if I detect in the other arm, and this other detector clicks, I get this kind of minus sign there. And so then you have to send a signal backwards to inform yourself. It's called feed forward. Which of those states did you produce? So you have to do a bit of bookkeeping on that. One of the things that's interesting about this scheme is these paths here related to the phi 1 and phi 2 can both be very lossy. And so you can have a lot of loss in the system, but as long as you get this click here, it tells you, yes, we succeeded and generated entanglement. So that's one of the nice things about these type of DLCC protocols is it doesn't always work. In fact, most of the time it fails. But when it does work, you get a signal that tells you, yes, proceed with the protocol. Now you have entanglement. And it really turns out that that's one of the key requirements for any kind of quantum networking. Loss turns any kind of deterministic system into a probabilistic system. So you need to have a signal at every step of the way that tells you, yes, we've succeeded, now move on to the next step. And that's really what this heralding does, is it allows you to overcome loss. You trade loss for rates, but you know when you have entanglement at your end stations. Okay. Any questions about that so far, or thoughts, or anybody want me to clarify anything? Okay, I'll move on then. So what we have, our requirements are that each of those photon sources from the left and the right, they have to make indistinguishable photons, because there can't be any knowledge about, did the photon come from like the left side or the right side? You have to completely erase that information. So it means the photons have to arrive at the same time, and they have to be indistinguishable in every way, like their polarization, their bandwidth, temporal envelope, like all of that has to be exactly indistinguishable. The other thing we talked about is for every single step of the protocol, when you do something, you need to have some kind of success signal, which we often call a herald, like you're heralding the next step. And finally, oh, I guess a few other things, the photons in these links here that stay in your kind of local labs and don't go over, whatever messy fiber in your metropolitan network, those photons that stay in this lab have to be very low loss. That whole path has to be low loss, because loss ends up decohering your system, because now you're taking the ones in this 1-0 term to a 0. And so you have to be very efficient. And that's really true of any of these kind of protocols, even the atomic system ones. So you need to have very low loss in these arms.
Could
Yeah,
I ask a question?
please.
So the optics and like the surface coatings and generally things like that are needed to actually carry these out, are those good enough to not have effectively like the photonic yield cause a lot of issues? Or is that an area that really needs to be worked on, as well as the heralded photon delivery and measurement?
Are you talking about these links here, or
More of
the
like
ones that stay in the lab?
yeah, like the ones that stay in the lab even.
That is something that we've been working hard on, and we're targeting 10% system loss. So from the time that a photon is produced, and if it goes on this arm, all the optics it sees, including coupling from free space into a single mode fiber, and then hitting the detector, and including the detector losses, everything else, we have, we're trying to get above, we're trying to stay below 10% loss or 90% total system detection efficiency. And
Yeah,
we've been able to demonstrate that in the lab.
I didn't know you could do that well coupling into a fiber like that. That's awesome.
We've had to invent our own fiber coupling techniques to make that happen.
Are
That's
there
usually the
papers or
thing.
anything on that I could read?
No, I've been meaning to make like a YouTube tutorial about how to actually do that. So I've been trying to convince one of the grad students to do it. But at some point, we'll probably put out a short little technical paper of just how to do it. You have to take, and I'm happy to also chat with you at some other point about how we do it. So there's a few, we've been working, but this is a big.
It's not trivial by any means, from my perspective.
Yeah, and I want to mention, I think really something that we need in quantum networking that you don't have to be a quantum networking expert in is we just need ways to take our classical devices and reduce the loss, because we have such tight loss budgets for a lot of things. So when I call up a company and they say we have a low loss 2 dB whatever device, filter or modulator, that's already game over for us. And so we really have to work hard to, in some cases, just do a lot of stuff ourselves that I think hopefully quantum networking, if it becomes a bigger industry, it'll motivate companies to actually start doing this. So yeah, this is something that we spend a lot of our lives in, is just trying to figure out how to reduce every 0.5% of loss in the system.
And I assume you guys have budgets. Are any of those published in the chat? Olivier and I were both interested in if there's like numbers we could attach to what you guys are doing.
Yeah, so I didn't have the slide here, but so for example, the protocols, it depends on the protocol you want to run. So for some sensing things, you can actually tolerate quite a bit of loss, like 50, 60%, that's fine.
Yeah.
For some of the next generation quantum secure communications that we're trying to do, where you really need to generate entanglement, high quality entanglement between these two stations, and then be able to run these what are called device independent quantum secure protocols that have a provable quantum advantage. I mean, it's a nice thing because if it works, there's no classical system that can do that thing. Like, it's a proof, like unless you can send information faster than the speed of light. those have very tight loss tolerances,
Mhm.
and they tend to be no more than like anywhere from, depending on your protocol, 15 to 30% loss. Like
Mm,
33% loss is like the absolute maximum you can tolerate.
okay.
Some of them it's like 15%. So, and it's a type of thing where if your protocol can tolerate 30% loss, but you have a bit of dark counts in your detector or something like that, you really need to be up in the 70s or 80% efficiency range for like
Yeah.
your whole system. And so we're targeting 90 for that. And then you can unambiguously show you have a quantum advantage. All the systems I showed before, like those networks, can't even come close to doing, like, they don't meet these metrics. They're not good enough.
Yeah.
So
Is there a published budget? Have you guys?
it's, yeah, if you look at our device independent protocol papers on
Okay.
randomness generation and a few other things, we go through, yeah, you can look at how things scale there.
Nice. Thank you.
And so some of the things we do need are high efficiency single photon detectors, which our lab is really good at, and I'll mention those in a second. And we need to make sure that the phase is stabilized really, really well. And so to give folks, an idea, we're going for, if you want to use the like the femtosecond or 10 to the minus 15 optical clock analogy, what we're going for is more like an attosecond level of stabilization. So you got to, bump things up like 2 to 3 orders of magnitude in stability. So because we care about high frequency noise, and it's a challenging thing. But I think Tara, who I think is on this call, is really kind of working hard to help us develop those type of systems.
Hi, Krister, I'm here.
Oh, great. Okay, good. So Tara can jump in and answer all the hard timing questions.
Okay, yeah, I'm around.
So again, a lot of the stuff that we're trying to do is based off of the time transfer that has been developed here at NIST for linking these optical clocks. And can we take this and make this even better? So this is the 2021, the Bacon, I think it's the Bacon collaboration paper, and where they use this kind of Boulder Research Area network, the brand fiber, to connect down here in this corner, that's the JILA location with the NIST location, and do this amazing, 18-digit accuracy optical clock network. And we need to take some of those ideas and extend them to make them even more precise. So some of the things that we have here at NIST that we've been working on are really great photon sources. And so I specialize in this process of down conversion, where you take a pump photon, interact it with this nonlinear material, and it produces pairs of daughter photons. This is called spontaneous parametric down conversion. It's been around since at least the 70s, maybe even 60s. And it's the workhorse for a lot of quantum optics experiments, because you can produce pairs of photons out of it. The other technology I'm going to highlight are these kind of quantum dot technologies that the idea is you make like an artificial atom with these defect centers, and there's a few ways to do it, but you then put it inside of a cavity, and you can control the cavity. And then every time you excite this cavity, you get a single photon out. And so these are really good, efficient single photon emitters. Right now, the problem is these photon emitters, getting these photons coupled into fiber, the best that's been demonstrated is about 70% efficiency, which is already not good enough for what we need. So if these come along and develop and become better, we'll switch to them. But there's a lot of active work to try to get that up into the 90% regime. And there's a big gap going from a 70% system to a 90% system, and then a huge gap going from 90 to 99%. And these systems also, if you take two of these quantum dots, the photons coming out of them aren't perfectly indistinguishable from one another. There's distinguishing information that really limits their usefulness right now for these style of quantum networks. So we're using this kind of, I call old school technology. It's bulk. You have to use pump lasers to come in and produce these down converted photons. But we're very good at fiber coupling these systems. And we've done a lot of like both modeling. We've got a free tool online called SPD Calc, that .org that does all of the modeling for you for these systems in terms of fiber coupling and whatnot. So, here's the kind of, not for this particular setup, but these are fairly typical numbers we can get, like close to 90% right now. And we've got ways I think we can boost this up to 90 or 92% efficiency for our fiber coupling. And part of this is enabled by these amazing detectors, these single photon superconducting nanowire detectors that our group has pioneered and helped develop. And so my colleague Dilip Reddy has made these detectors that are now like 98% efficient. So we'll detect 100 out of, if you put 100 photons into a fiber, 98, you'll get 98 clicks. So that includes the fiber losses and coupling, like once you're in fiber. So, these are some of the different detector technologies we have available. These avalanche photodiodes, they're not very efficient, but these nanowire detectors are very efficient. And then there's also another technology called transition id sensors that can also do number resolution. But these are they're very painful to work with and they're quite slow. So we're really operating on the nanowires and trying to get some limited amount of number resolution in them. And these are now at a very high technology readiness level. There's like a dozen companies or so around the world selling them. You can buy them, they're commercially available. And you do need some cryogenics to get down to 1 Kelvin, but people are now trying to push up to 4 Kelvin to make the cryogenics even better, and they're quite robust.
So for these methods, you'd have to have those fiber cables going into like a cryostat.
Yep.
For these detectors to work. Okay.
Exactly. And again, like all of those losses and the total detection efficiency, including the fibers and whatnot, that's still like 98%. So that's really good. And, we've been able to, I'd say in 2015, we established some simple entanglement distribution over very short distances. So we didn't have to, worry about losses too much from like the fiber cables. It's only 100 meters. So there's like a negligible amount of losses. And we're able to do these device independent protocols. And we've done some of these. So these are some papers that I'd recommend, taking a look at if you want to get some of the bounds on how these protocols scale with loss. And so for these experiments, we create photons in this bulk source right here. It's in free space. We couple the photons into fiber. They go through a bunch of optics. They couple into fiber. They travel down these fiber cables, and then they reach these end stations where they come out of fibers, and then they're measured really rapidly. And then they couple back into fiber and go to our detectors. And essentially, we only have about 17% loss, even though we have multiple fiber coupling stages. And we've worked really hard to kind of get all these losses to a manageable level. For the network that we're building and the kind of protocols we want, there's nice schemes that we can actually reduce those losses even further to get to that 10% level that we're targeting of loss. And just to kind of plug, we also have some amazing detector technology, those nanowire detectors that are really efficient. We're now trying to build cameras out of them. And so part of our group makes these amazing, large scale pixel arrays where, eventually you'll be able to read out each pixel individually in real time and be able to resolve, do kind of real time analysis of like single photons. So there's a lot of technology we're using and kind of pushing on for, dark matter detectors, for space comm. We work with the Jet Propulsion Lab, JPL, quite closely with this, and also just for bioimaging. There's a lot of interest for these detectors. So coming back, I want to mention a couple of other things about like the schemes that we're setting up. So what we're proposing to do is to take this down conversion process where we produce a pair of photons from each side. And this process is probabilistic. So, typically about 1% of the time that we try, so we run in a pulsed manner. We have a pulsed laser that's running at 100 megahertz. So 100 million times a second, we're trying to hit, produce photons, but only about 0.01 or 1% of the time does a pulse actually produce a photon. And so what we can do is we need to know when that happens. So we're going to use one photon as a herald, as a detector. And so what we need to do is when both of these heralds go off, we know that we've produced a photon on either side. That says proceed to the next step. And then what we can do is we get a click here, then, you know, we generate our entanglement like before. And so, unfortunately, this really hurts our rates if you have to wait for all the sources just by chance to fire. But so I'll talk about a way to mitigate that in a second. We're going to add memories to it. But we've been working really hard on taking the kind of large entangled sources that we've developed and really trying to turn them from something that you need multiple grad students and a lot of time on PhDs to kind of make work to more like a table, like you know, something you could put in a 19-inch rack mount box. These are some of the mounts that we're developing to try to you know, make everything much more robust and more compact and high efficiency, so you can start, you know, making many copies of these. So that's one of the technology engineering things we've been pushing on. And so a way that you can kind of improve the rates is to instead, what you do is you add a memory into the system. And since the memory has a bit of loss, we'll put it into these channels that can tolerate loss. And so what happens is now when we produce a photon, what we do is we switch the memory such that the photon goes into like just a little storage loop here. And you can use the polarization degree of freedom to keep the photon trapped in this loop, and then use an active device like a switch or Pockle cell or some other device to change the polarization quickly to release the photon when you want. So what you do is you wait and you get a photon on this side, and then when this side also fires, it gets a photon, then you're both ready on either side, and then you can release, you know, whatever's in the memory, and you know, you improve the success rate dramatically. So this can actually, that's a scalable approach to turn something that's a probabilistic source into something that's nearly deterministic. So we're working with a colleague of ours, Paul Kwiat. His students are actually forming a company around trying to build these memories, which it's just FPGAs and time tagging modules, and you essentially just take your photon in, and it just goes around this like polarization sign. Well, it's not a sign; it's just in one direction. This loop, and then you flip the polarizer or the Pockle cell when you want, and then the photon gets emitted into the rest of your system. So simple technologies, and for time delays of up to about, you know, say 1 to 10 microseconds, this just vastly outperforms any other kind of atomic memory in terms of fidelity and loss and everything else, just as bulk optics approach. So then another thing we need is that kind of phase stabilization, because we really need to be able to make sure that, you know, the accumulated path length on any of our fibers, like collectively, doesn't drift by more than, say, 10 nanometers over the course of our measurements. So I think that's like, like 10 hydrogen atoms or so of path length change that we can tolerate, which is a little challenging over kilometers of fiber. And so what we're really trying to do is add in some extra components where we can take these pump lasers and lock them as frequency combs to help track, you know, drift, and use some of the same technology for both our local oscillators, and also lock these two frequency combs to make adjustments, and then do some kind of ranging on the scheme, on the setup to actually, you know, get that high level of phase stabilization. And that's much higher than like what other groups are currently able to do. So this is kind of the scheme, and we've been working with Tara and her postdoc Nick, who have make these really incredible 1550 passively mode locked lasers, and they use these kind of CSAMs as the kind of mode locking device. Really stable, quite amazing, and you can lock these to like a reference, like a stable reference laser, to turn them into basically a comb. And so that produces the light that we need for our down conversion. That's at 1550. We have to send it through second harmonic generation to turn it into 775. Hits this crystal, and then we get a pair of photons out at 1550. So altogether, these technologies allow us, just with existing technologies, to really try to go after this. And one of the big advantages is, we should be able to do this over the Boulder Research Area Network. That same fiber that was used in the earlier clock demonstrations. We have a lab at CU, the engineering department in Boulder, and over at NIST, and we're going to be setting up these sources on either side. And we should be able to get entanglement generation rates, in the kilohertz type regime versus millihertz. And the fidelity of these isn't going to be 60%, but we're really kind of targeting swapping fidelities in like the 99% range. And so very, very high quality, and that allows us to actually do quantum protocols, non-trivially, these kind of next generation quantum protocols over meaningful distances in a urban environment.
Do you guys have a timeline for when those experiments are going to start being run? Are they being run now? When will the public have access to, information on how successful this demonstration is?
So our current timeline is, I'd really like us to be able to do the first sort of demonstrations of this in about 2 years. That's
Nice.
kind of it's an academic environment. We don't move as fast as companies, but, right now we're really close to getting these new source designs that there's a lot of source engineering we've needed to do. That where everything's locked together with the local oscillators and these combs and stuff. We've been working very closely with Tara's group to kind of build a system where everything's integrated from the ground up. I think something that's overlooked is, with quantum engineering, we often think about well, somebody's got this part of the problem solved here, and someone's got this piece of the problem here, and I'll just like smash those two things together, and that's a solution. And my thought is, it's always like saying, to a biologist, like, well, we know horses exist and we know rhinoceros exist, so it should be trivial to put them together to make a unicorn. That's just not how the engineering works. It has to be built from the ground up. And so this is something where, we've been trying to learn more about time transfer techniques and the kind of state of the art of stabilization. And folks like Tara have done a great job of coming in and learning the quantum side, and we're trying to engineer something collectively. And it took a long time for us to even agree on like what we meant by phase. There's just communities that speak very different languages. And I think there has to be a lot more co-design in these systems to make them successful.
Cool, thank you.
So I'm going to get to your question now. So these are some measurements that Nick Nardelli, Tara's postdoc, did over kind of just, you can take the noise accumulated in a system, so like and you can integrate that to kind of to form like an equivalent timing error. And we're really targeting to get to our 99.5 or 99.9% visibilities. We're targeting kind of like the 10 to 40 attosecond range of accumulated timing. And so here's what I find amazing is doing a little loop out and back on 7 kilometers of this brand fiber, right? Just the fiber itself is passively stable for quite a large time window. And what we're hoping to do is be able to run this protocol. It's going to depend on the particular fibers, where you can have a window where you don't do any active stabilization. You just let it free run. And then what you do is you go to a stabilization window and stabilize. And so what we're trying to figure out now is, how many photons do you need in that stabilization pulse? Because you can't just send a milliwatt of power down, that overwhelms everything. So you need to do this with low power and keep it as short as possible so you can keep the kind of effective quantum duty cycle going. And we have some ideas for how to do that. But it's surprising to me how stable this is. And also, I think a lot of this noise is actually just from the laser that was being used. So it could potentially be quite a bit better than this.
And
so go ahead.
sorry, one more question. Is the fiber you guys are using for this, is the goal here to have this operate on existing deployed fiber? Or is this the kind of thing where like hollow core fiber or novel fibers might help?
They might help, but for the first sets, we're trying to do it over dark deployed fiber.
Cool. Thanks.
Just wanted to mention, I'm going to maybe in the interest of time, because we're almost at the end, I'll just kind of skip these two things, but you can take these kind of repeater ideas and you can start cascading them where you wait for, you break your network up with multiple links into a left-hand side or right-hand side. You wait for one stage to succeed, and then you wait for the other stage to succeed. You store the results, and then when they both succeeded, then you go on to the next stage. And doing this, you can actually create this kind of cascaded binary tree that allows you to do these type of networks. They scale non-exponentially with loss, which is good. So just want to throw that out there if anybody cares about scalability. And, just our technology development for the next 2 years, we really trying to, we want to get to like a pretty high heralded photon pair rate per second. And first, we're not going to use the memories. We'll integrate that into like the 3-year kind of mark. And so these are some things that we're trying to develop right now in the lab. And we've made quite good progress on a lot of these areas already. And eventually the kind of goal is to start making more connections. So this is just on the university campus with NIST, but then start going to the rest of the Boulder Research Area Network and start trying to connect to other places in Boulder that we might be able to set up these deployed nodes as well. And so we'll have to work on getting the technology more stable. I guess that was pun unintended, but and a little bit more robust to set these up across the city. So I just want to end with, we really have some initial test cases for metrology that should tell us how good these networks are and how good the entanglement is, based on how good the whether or not we can actually carry out protocols that have a demonstrated quantum advantage. And I really think that by pushing on these kind of the boundaries of the technology, the real application space, it's a bit like an iceberg, right? Like the top 10% that's visible above the ocean, and that's the quantum motivation for trying to make these technologies better. But I think lower loss devices, better stability, being able to do everything plug and play with low light losses that don't interfere with your other kind of traffic, all of that's kind of like the 90% of like the classical kind of enabling technologies that will have lots of other kind of spin-outs. And so I think for technology development, these are some of the things I'm excited about. So I'd just like to end with this slide of some of the collaborators and people that we're working with. And we're always looking to form other collaborations and partnerships with other folks. So thank you.
That was really great. Thank you.
Yeah, thank you very much, Crystal. Excellent presentation. I have a question for you. When Tara did her first presentation in this series of talks about quantum communication networks, she highlighted some few challenges, like single photon sources for distributing quantum states, quantum memories, single photon detectors. So how much progress have been achieved in NIST in overcoming these challenges?
So I would say the detectors, we figured out schemes now that I think we're basically there. We have the technology to do our first set of demonstrations. That's not our bottleneck. We're also working, on like 2 or 3 different generations of detectors at once, like at different timescales. And so I think the detector technology is extremely well understood. And there's some things that are nice to have that we're trying to develop, but not necessarily essential right now. In terms of the quantum sources, this is something that we have right now. We're setting up and doing the detailed kind of metrology and characterization. So I don't want to say too much because we haven't finished those measurements, but it looks like we have sources, I will say, that are going to be good enough to do this, like that are indistinguishable enough and can interfere with high probability or high quality, and also can be locked and stabilized with these combs because we're pumping directly from them. So we've been doing a lot of work on that. And then in terms of link stabilization, right now we're trying to do the detail, like Tara and her group are doing all of the detailed characterizations we need for that. And I think that's on really good track as well. So I think we're making really good progress on all of these areas. And again, it's all kind of simultaneous. And something I didn't mention, but we've got a really strong set of theory collaborators, and the theory collaborators have also really been adapting a lot of the protocols that we need for these kind of path entangled photonic schemes. And what are the measurements? What are the optimal set of things you have to do? So,
And as far as time synchronization is considered, you said we need maybe 2 more years to report some progress.
I think we need 2 more years to do the demonstration, like this level of demonstration, where we're actually, the measurements are all happening and everything's synchronized. And, so we have the synchronization of photons, being emitted on the same clock and arriving places at the same time, but also the second level of synchronization, which is you're compensating for path length drifts in all of the fibers and paths down to the, like with attosecond kind of precision in terms of keeping the interferometric stability.
So thank you very much. Anybody has any questions for Krister? If no questions, then thank you very much, Krister, and this was very informative presentation. And thanks for everybody for attending. Thank you.
All right, thanks for having me. Take care.
It's a pleasure.